Since scientists made the surprising discovery of two planets orbiting a star outside our solar system in 1992, thousands of new worlds have been added to the growing list of exoplanets in our Milky Way. This discovery was so impactful that it changed the way we see the universe and our own existence. But as we explore these distant worlds, one detail stands out like a sore thumb. So far, we haven't found anything similar to our own solar system. This leads us to question, are we really the only ones with a home like ours? Is life really rare in the vastness of the universe? If we just look at the numbers, the chances seem small. Most of the exoplanets we've found so far are gas giants or subgiants with conditions unfavorable for life as we know it. Additionally, most of these planets orbit very close to their stars, exposing them to unbearably high temperatures, indicating that if there is life somewhere, it's not that common. As we continue exploring the universe, it's possible that we'll find more places that remind us of our own home. But the truth is that this question is much more complex than just looking at the numbers. The science of exoplanets is still in its infancy, and our technology has limitations. Moreover, our perception of the real diversity of alien worlds may be limited by our own imagination. What really exists out there in the Milky Way and beyond may be very different from what we can see so far. The history of exoplanet science has been surprising since the beginning. When we were kids, we only knew of one planetary system, our own, and it was our only reference, so we thought all planetary systems would be like that. Rocky planets close to the star and gas giants far away from it. But the truth is that the universe is much more complex than we imagined. For this reason, scientists took some time to find an exoplanet orbiting a star like our Sun. They deduced that other solar systems would be like ours, so revealing signals of heavy planets pulling on their stars would take years to observe, just like our own gas giants take years to complete an orbit. And when scientists started searching for planets outside our solar system, they encountered something completely unexpected: a gas giant with half the mass of Jupiter and twice the size orbiting so close to its host star that its year lasted only 4.2 days. The atmosphere of this gas giant burned at temperatures of around 1,000 degrees, and this was a surprise because scientists expected to find something similar to our own solar system. But these planets, known as hot Jupiters, are not that uncommon. In fact, the galaxy has a lot of variety, and there is still much more to discover than what we see in our own backyard. It is important to remember, however, that what we can currently detect may not be all that the Milky Way has to offer. There may be star systems out there that are so similar to our own that we still do not have the technology to detect them. In the words of planetary scientist John T. Horner from the University of South Queensland, systems like our own are very difficult to find for us at the moment, as they are just beyond our technology. It is very unlikely that we will find terrestrial planets like Mercury, Venus, Earth, and Mars around a star like the Sun in our searches so far. This shows that the science of exoplanets still has a lot of potential to surprise. The methods we use to detect exoplanets currently involve two main methods: the transit method and the radial velocity method. Both require a telescope that can detect very small changes in the light of a star, but the signals they are looking for are very different. The transit method needs a telescope that can keep a star fixed in its view for an extended period of time. That's why instruments like NASA's Transiting Exoplanet Survey Satellite, TESS, are so powerful, as they can observe the same segment of the sky for over 27 days without being interrupted by the rotation of the Earth. They are looking for small variations in the star's light that can be caused by a planet passing in front of it. This way, we can detect the presence of a planet.
Unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that tests will allow us to find will enclose essentially all of the bright nearby stars.
These changes in light are very small, and a single transit is not enough to confirm the presence of an exoplanet, as there are many other things that can affect a star's light. Telescopes like this search for transit signals when an exoplanet passes between us and its host star, blocking some of its light. That's why it's necessary to observe several transits regularly to be sure. For this reason, larger exoplanets that are in short orbits, very close to their host stars, are the easiest to detect. Some of them are so close to their stars that they complete an orbit in less than a week. This makes them more likely to be found in the data. Another method we use to detect exoplanets is the radial velocity method. It detects the oscillation of a star caused by the gravitational attraction of an exoplanet as it orbits. In fact, a planetary system does not orbit a star, but rather dances in a complicated coordination. The star and planets orbit a mutual center of gravity, known as the barycenter. In the solar system, this point is very close to the surface of the Sun, or even outside of it, mainly due to the influence of Jupiter, which is more than 2 times more massive than all the other planets combined. While a transit is a momentary event that needs to be constantly observed to be detected, the change in the star's position is a continuous change. We can detect the movement of distant stars orbiting their barycenters because these movements alter their light due to the Doppler effect. This effect causes light to appear to change color depending on whether the light source is approaching or moving away from us. In addition to the transit and radial velocity methods, it is possible to directly portray an exoplanet orbiting its star. This is difficult, but may become more common with the use of James Webb. This method discovers a nearly opposite class of exoplanets compared to short-orbit ones, as it requires a wide separation between the exoplanet and its star to detail it without being affected by the mother star's brightness. This means that this direct imaging approach favors exoplanets in longer orbits. As we can see, exoplanet detection methods have biases, as they favor certain conditions. Where the transit method and radial velocity method favor larger exoplanets in shorter, closer orbits to their stars. Direct imaging, on the other hand, favors exoplanets in longer orbits. But there is still a trend for larger exoplanets to be more easily detected. This makes it difficult to find one-year orbit planets like Earth. Imagine you are a scientist traveling to the outskirts of the Milky Way in search of new planets. After years of searching, you finally find a promising planetary system. But when you look closer, you realize that most of the planets there have extremely short orbits, with more than half having orbital periods of less than 20 days. This is strange because in our own galaxy, Earth has an orbit of 365 days. And this is our reality, with most of the exoplanets found so far orbiting single stars like our Sun. However, most stars in the Milky Way are part of multiple star systems, with up to 80% orbiting at least one other star. And then researchers wonder if the presence of multiple light sources can distort the weak signals we seek to detect exoplanets, or if it also considers the possibility that multiple star systems may complicate planet formation in some way. Back in our home in the solar system, something else may seem strange. The fact that we have not found some common types of planets in other planetary systems. According to Daniel Bayliss, an astronomer at the University of Warwick, UK, there are some very common types of planets that are missing in our solar system, such as super-Earths and mini-Neptunes. However, this does not necessarily mean that our solar system is rare. It is possible that there are many other stars with sets of planets similar to the solar system that we have simply not detected yet. The first exoplanets were discovered just 30 years ago, orbiting a pulsar, a type of star very different from our own. Since then, exoplanet detection technology has rapidly advanced, allowing scientists to find these worlds around an increasingly wider variety of stars. And as technology continues to evolve, we will develop the ability to find smaller and smaller planets. This means that the science of exoplanets may be on the brink of discovering thousands of worlds that are currently hidden from our view. In fact, in astronomy, there are many more small things than large things, such as red dwarf stars, the most common type of star in the Milky Way, responsible for up to 75% of all the galaxy's stars. And many researchers believe that at the moment, we are still working with incomplete information about exoplanets, as there are types of worlds that we simply cannot see yet. Horner came to say that, this irritating feeling that if you come back in 20 years, you'll look back at statements that mini-Neptunes are the most common type of planets, with as much certainty as you would look back at statements made in the early 1990s that there were only rocky planets close to the star. However, he admits that he may be wrong, as that is how science works. But still, he believes that when we get to the point of being able to discover Earth-sized and smaller planets, we will discover that there are many more of these types of planets than Neptune-sized planets. And who knows? Maybe we will discover that our own peculiar planetary system is not as alone in the universe as we thought.